in problem 12.41, we have a ladder that's placed against the wall, and we're to find the mass of the maximum mass that this ladder can support without slipping for a person who's climbed to the top of the ladder. The forces involved here are the friction force, which keeps the ladder from slipping at the bottom. So there must be a normal force applied vertically to support this and to keep the object from sliding, or the ladder. There's a normal force up at the top of the ladder pushing horizontally. Here's the weight of the person at the top exerted down onto the ladder. And here's the center of mass of the ladder. That's got to be a normal, a force downward. The ladder is length L. And in order to be able to determine this, we must assume that equilibrium is still established for that person of maximum mass. Now, the information given about the ladder and the masses are over here. It's got a certain length. The angle is 66 degrees. Here's the mass of the ladder, the coefficient of friction, the length of the ladder, and the distance of the center of mass from the bottom down there, and that's just L over 2. Now the unknown is the mass of the person at the top. And of course, to be able to determine this mass, we must be able to establish the maximum mass such that it's an equilibrium. That is, the sum of the forces in the x must be equal to 0, the sum of the forces in the y must be equal to 0, and the sum of the torques. About this point at the bottom, and that's where I'm going to calculate the torque, the point about which the sum of the torques must be equal to 0. We're going to have to find that friction force and the normal force in the x direction. So if you sum the forces in the x direction, then the normal force in the x direction, and that would be negative, plus the positive force F sub F in the positive x direction, they must add to be 0. So the normal force in the x direction is nothing more than the friction force. The normal force in the y, the vertical force, and you can see that over here in the free body diagram, that minus the two weights must add up to be 0. And then finally, to find the torques, summed about the point at the bottom down there, you have the torque of Fn x, and that's applied at r sub m, vector r sub m. And the angle between those two, I've labeled this as angle alpha. So that torque is Fn times the distance r sub m times sine alpha. Now, and by the way, that is a torque out of the board here. So I'm going to call that that's the positive direction. Then you have the large mass here, which has a torque equal to the distance from the origin times its magnitude, mg, and then times the sine of this angle. Here's the angle between r and rm and mg. This I call that angle beta. And likewise, the center mass of the ladder, mg times rm, there's its distance. The angle between those two is beta also, so I multiply by the sine of beta and set all that's equal to 0. To determine get all these angles in terms of theta, you can see that alpha and theta are supplemental angles, so the sine of alpha is equal to the sine of theta, so that's where I've replaced that here. And then you can see that beta and this unknown angle, I didn't give it a symbol, they're supplemental angles, so the sine of beta is the sine of this angle, but that's the cosine of theta because they're complementary angles, so I went ahead and just put in here cosine theta here for the sine of beta in both places, collected terms. Then all we need to do right now is get rid of this Fnx, get it in terms of the weights. And we can do that because the force of friction is mu times Fn in the y direction, and Fn in the y direction, due to this equation right here, you can see is just equal to the sum of the weights pushing down on the ladder vertically. So if we multiply Fny by the coefficient of friction, then we get the normal force in the x direction. And that's what we can put up here in this term up here. And that gives us mu times the sum of the masses times g, and then times the r sub m is just equal to L, so I substitute that in and put the sine theta there, okay? So that's got that term. And then these two terms, I've just brought those down right here, where I factored out the L and the L over 2. That's what these two R's right here, R m and R sub m, R sub center of mass, that's just L and L over 2. So if I bring the masses down and the values of R sub m and R sub center mass, those terms go in there. And then all I've done in the next term is just begin the process of isolating the mass of the person sitting on the top of the ladder. So all I've done right here is just expand, well, gotten rid of the G's and the L's, and then expanded this term right here. Okay, so that's m over 2 times cosine theta. Okay. Also, it looks like I've inverted the sign too. Okay, so and then we've got the mass of the person times cosine theta, and then minus mu times the sum of the masses times sine theta. I'm going to stop at this point and let you solve for m here. It's just a bunch of algebraic manipulation, and you should be able to get, after you've got that isolated for m, then you should be able to plug in the values and get the correct answer.